Okay, so in this section, we're going to take a look at disease as it existed in prehistory. And we've talked a little bit about prehistory. We've noted that that's everything prior to writing. And just to be a little bit more specific here, in addition to that disease in prehistory, and we're looking at that period that's prior to the invention of writing, we're looking specifically at an epoch, a geological epoch. Now, remember, geological epoch, this is one of the ways within which we see time as it's progressed, the course of time in world history. So we have a geological epoch, and we're interested in the Pliocene and the Pleistocene. The Pliocene refers to approximately 5 million to 2.5 million years ago, and the Pleistocene, that's 2.5 million years to approximately 20,000. So we change that to we're going to want that in millions of years. So 20,000 years. Write this in brackets over here. 20,000 years before the present. That's transcribed as 0.02 MYA. Now, one of the things that you might be, and you should always be asking these types of questions, is ultimately, how can we comment about disease in prehistory? Aren't we just looking at material as we see it through the fossil record? Absolutely. We're looking at the fossil record, and sometimes we are able to find small amounts of biological matter in these individuals' teeth, in the teeth of the fossils, and that can be extracted. So as pointed out, we're going to take a look at disease in prehistory, or in the prehistorical period. That's everything that occurs before writing. We're looking, or we're interested in, a couple of geological epochs here in particular. Number one, we're going to talk about the Pliocene, where we find our oldest bipedal ancestors, and we're interested in the Pleistocene. And the Pleistocene is important because this is where we see the emergence of stone tool technologies. So that ultimately marks the Paleolithic, and it indicates a shift in our dietary patterns. And you can imagine, as we began to shift in our dietary patterns, that opened up the possibility to be introduced to new disease-causing organisms. Okay, I'm just going to erase this now. Hopefully a little bit faster than this, and we can take a look at a couple of points that I have prepared. And I'll just remind you as I do this, if you have any questions, fire those off in an email, and I'm going to try to have, again, some more Zoom meetings where I can address the issues or the questions. Hopefully no issues. Everything's, I think, pretty much straightforward here. But either way, that doesn't mean that you won't have questions. Don't be shy. Always ask questions. Okay, so paleoanthropology. A few words about this. Paleoanthropology is defined as the study of old humans. So we get a couple of words here in Greek: paleo, which means old; anthropos, which means humankind. We change that. And logos is the study. And then we just reverse all of that. We have the study of old humans. So we have the science that studies old humans or early humans, what we refer to as hominids, through the fossil record. Now, I'll just briefly say a few things about this term hominid. When we refer to a hominid, what we're referring to is a species that fits into our ancestral or evolutionary line. So Australopithecines, they would be hominids, but there's a whole group of Australopithecines. I'll just write that up top here. So Australopithecines, they're what we would define as a hominid. But because not all of them led to the human line, we have a special term that we want to use for those hominids that led to us on that evolutionary line, and we call them, I'm going to write it just up here, a hominin. Okay, so we're hominins. Homo erectus would be a hominin. Homo habilis would be a hominin. A chimpanzee would be a hominid. It is not a hominin. It did not lead to us. One of the ways that we get at the past, actually the way that we get at the past, is through fossils, and we just define fossils as inorganic impressions of the past. So the images we're seeing here on the right-hand side, they're what we would refer to as a cast of organic life. In other situations, we get an imprint, and those are probably the fossils that you're more familiar with. If you open up, for example, a piece of slate, you might see a fossil, an impression of life that was there. So as pointed out, then, fossils provide us with one type of evidence. We can look at those fossils for signs of trauma. We can look at the fossils for signs of disease. As I've already pointed out in our introduction to this, we can see cribroorbitelia. We can see osteolytic lesions, osteoblastic lesions. So all those different types of growth, and a lot of that stuff is particular to certain diseases. In addition to that, we can also look at the paleo environments. And here we're interested in what did the Paleolithic and pre-Paleolithic environments look like. And just roughly, I'm going to sketch this out again. So 5.2.5 MYA, we have the Pliocene. And it's always good to rewrite things. It's a great way to remember. So if you're working along with me, 2.5 to 0.02 MYA is the Pleistocene, and of course the Holocene begins at 0.02 MYA to the recent present, and here I'm going to say about the 1800s, and that's when humans started to have a profound impact on the environment. And if we wanted to sketch out climate change, what I'm going to point out, and a lot of people, I'm going to do it in two different colors here. So a lot of individuals think that our climate change as we currently have it, it looks something like this, maybe fluctuated in the past, and now we get to the 1800s, and now we're starting to see a significant rise in temperature over time as a result of humans. That's the model that we're often told. I'm going to tell you it's not the actual model of climate change over time. The Pleistocene was much warmer than it is today. In fact, on average, probably about 10 degrees warmer in some areas, so quite warm. So it kind of looks like this, more or less, time. And we have periods where we've gone into cold, very cold periods, ice ages, and we've come out. And yes, humans have played a role in climate change. We've caused a spike since the 1800s. There's no question about that. But there have been much warmer periods of time, and there have been much cooler periods of time. If we take all of this into consideration, we can gain an understanding of the types of diseases that would have affected individuals. For example, malaria. This is responsible for a child in Africa dying approximately every 2 minutes. And the question is, has malaria perhaps always affected our ancestors? Well, we can take a look at it by going to Africa and ask about that paleo environment. Was it warm? Was it cold? What was the temperature like during the Pliocene and during the Pleistocene? And what I'll tell you is it was, and we can see here, it was much warmer. So as for mosquitoes, at this point of time in Africa, I'm just going to write over top. Mosquitoes certainly thrived. And they're much older than us. Mosquitoes are about, I think, 150 million years of age. The other question we would have, well, now we have to draw upon a little bit of biology. So we have the vector. That's definitely present if we're looking at disease in the Pliocene. So that disease will be present. Sorry, that vector will be there. But what about the organism or the plasmodium? Plasmodium falciparum. Just rolls off the tongue, doesn't it? Plasmodium falciparum. That's approximately 50 million years of age. And what we know, anthropological research and evolutionary biology tells us that it probably spilled over from gorilla or gorilla-like, their ancestral populations, somewhere around 8 million years ago. That's when it started to affect our ancestors. So we're going to go ahead and say that during the Pliocene, malaria, it did affect our hominin ancestors. There's no question about that. So this is the type of research that we're doing in this area. We're going back in time and we're able to say something about health in prehistory, and perhaps, I think most importantly, begin to challenge some of the narratives that have existed historically about disease. Okay, let's move on. So in addition to currently being in a pandemic, COVID-19, we know that there's an excess of disease. We've talked a little bit about tuberculosis. We know that half of the world is infected with TB. There's a burden of diabetes, obesity, heart and stroke disease, cancers. That stuff continues to impact us alongside of newly emerging diseases. What did the epidemiological landscape look like prehistorically? Let's ask the question, has disease always been a problem? And if so, what types of diseases existed? And if not, why? Let's move on to the next slide. In Chapter 7, I remind you that the Earth has constantly undergone changes that have affected and shaped the lives of our ancestors as they do today. So here we're looking at continental drift. If we understand continental drift to involve the movement of the Earth's plates, we also have to understand that climate has been changing drastically over the last 800 million years, for example. Now I want to look at specifically the emergence of our more recent hominin ancestors, the Australopithecines, which takes us back about 5 million years ago. So let's look at evolution in these old or paleo environments and try to understand what types of diseases would have existed at this point of time. A little bit of terminology review here. So we have the Pliocene, 5 million to 2.5 million years ago. And this epoch, this geological epoch, was dominated by the Australopithecines, and around 2.5 million years ago, we saw the emergence of the first Homo species, Homo habilis. That takes us to the Pleistocene. The Pleistocene, 2.5 million years to around 0.02 million years ago. This geological epoch saw Homo habilis. It also contains the Australopithecines. They're continuing to progress through time. We see the emergence of Homo erectus, and we see Homo heidelbergiensis, Neanderthals, and eventually Homo sapiens sapiens. So this is a really eventful time, for example, for just the sheer development of hominin species over time. It also saw an ice age, and towards the end of the Pleistocene, we have a warming trend. That brings us to the Holocene. So the Holocene 20,000 years ago, or 0.02 million years to the present, this is a warming trend. So one of the ways that we could tackle the idea of disease and our ancestors is look primarily at the environment and what types of organisms would have thrived in the environments of the past. Let's move to the next slide. So if we try to build an understanding of the epidemiological landscape that our ancestors lived in, there's a number of considerations that we do need to think about. For example, what was the average group size of our hominin ancestors? Did they live in the thousands, tens of thousands, 200,000 individuals? Absolutely not. These were nomadic groups of individuals. They had territories, and their population size would have been small. Now, that would have an impact upon their epidemiology or the distribution of disease in those groups. Imagine if you've got a small group of individuals and they contract, say, a highly virulent virus, it's going to move through that population really quickly. And in all likelihood, if it's something like, say, Ebola was in 1976, it's going to wipe out the entire population. In wiping out that small group of individuals, that virus also wipes itself out. It disappears unless it has an avenue to get out of that particular group and infect another group of humans. So this is where that term endemic, for example, is pretty important. For a disease to remain endemic or within a population, it always needs fresh, new hosts. So group size, generally speaking, with smaller groups, we don't see the persistence of disease that we do today. In addition to group size, we have to consider dietary patterns. What were the dietary patterns of the Australopithecines, for example? Well, they were vegetarians. Now, that doesn't mean that they didn't pick up bacteria as they were foraging, but some of those diseases that are transmitted through meat or that you can contract through scavenging, say botulism, that wouldn't have been present among them. As we start to eat meat, however, we're going to say yes, we have those diseases associated with meat eating, botulism, for example, salmonella. In addition to that, worms. That stuff is going to begin to emerge. So at what point of time did we start to eat? And now we're going to be able to eat meat. And at that point, we can start to say, yes, our health is changing in a different way as well. In addition to those dietary patterns, we have to look at the territory that these individuals live in. Do they live in forested environments? Do they live on a savanna? And if they live in a type of savanna, what types of organisms live there? Is there anything that could effectively transmit or vector disease to our hominin ancestors, such as the tsetse fly or mosquitoes? In addition to that, we need to take a look at the temperature of the environment. Was it right or conducive for the existence of mosquitoes? A lot of the mosquitoes that are responsible for carrying malaria, they live in tropical areas, and that's why we don't have issues with malaria in Ontario, for example. It's because those mosquitoes just don't thrive here. They can't live in this environment. So again, what was the environment like during these prehistoric times? In addition to our environment, we need to look at the ecosystem and absolutely the other types of animals that are living there and what types of diseases can be transmitted if they are, in fact, interacting. Let's move to the next slide. Here we have an image that depicts the early Pliocene environment that our hominid ancestors would have lived in, say, 5 to 2.5 million years ago. So we can imagine we have our Australopithecines here in addition to Homo habilis. Now, the paleo environment during the Pliocene, it was a minimum of plus 5 degrees Celsius warmer to approximately 10 degrees warmer than it is currently. Water levels were higher than the current conditions. We know that a variety of disease-causing microbes would have existed. They would have thrived in this type of environment. So what are we looking at in particular? Well, number one, if we look at the basic needs of any animals, they would have had to have obtained water. So in that type of situation, we have contact with waterborne and soil-borne microbes, for example, Giardia, schistosomiasis. In fact, schistosomiasis or Schistosoma mansoni, it does date back to about 5 million years ago when it became adapted to our hominin ancestors. And ever since then, it's continued to live alongside of humans. In addition to drinking or needing that water and being in those water sources, we also have contact with vector-borne microbes in the savanna, for example, mosquitoes, which transmit Plasmodium falciparum, and tsetse flies, which are responsible for transmitting trypanosomiasis. Now, how old are these organisms? Would they have been around? Well, Plasmodium falciparum is approximately 150 million years old. Trypanosomiasis is about 50 million years old. Mosquitoes, they again date back millions and millions of years. They predate our ancestors, so they would have been present. Evidence suggests, according to our textbook, that Plasmodium falciparum, it spilled over approximately 5 million years ago from gorilla populations or their ancestral gorilla populations to our hominid ancestors, and it has remained with us ever since. Now, did the type of morbidity or distribution of malaria exist then as it does today? The answer is going to be no, because we've changed the environment today and we've created a situation that allows for more malarial infections. For example, through clear-cutting forests or engaging in something called SWIDN, slash and burn technology. We'll talk a little bit more about that later on once we get to farming. In addition to contact with vector-borne microbes, we also have to consider that when we started to eat meat, we would be in contact with animals, possibly sick animals. There's no question about that. So our earliest ancestors, they weren't hunting, they were scavenging. Scavenged meat, an animal that had been lying there for a period of time decomposing. There's a number of health issues that we could imagine would be associated with that. For example, salmonella, botulism. In addition to that, some of these animals would have had worms. That's just a fact of life. For example, tapeworms and escarred worms. As pointed out in our textbook, again, this is another point that we can say as our diet began to shift, we have that behavioral change. We also understand that worms, tapeworms, became adapted to the human species as well. So we've been living with worms for a long time. When we look at this epidemiological landscape, however, we have to understand that the amount of disease or the burden of disease is limited. We don't have obesity, heart disease isn't present, diabetes isn't present, we don't have tuberculosis, that doesn't exist as of yet. We don't have smallpox, we don't have measles. All of those diseases that have affected us in more recent times, they're just not present. So I think to answer the question, was there a golden age? There's a little bit of hyperbole here. Yes, there was a golden age with a caveat. Disease existed, but not in the same way that it does today. Of course, it was around. Animals got sick. Diseases were passed on from one animal to the next. However, the burden was fairly low. Let's move on to the next slide. Let's take a look at a few of these organisms and the environments that they emerged in during the Pliocene. With respect to freshwater, Schistosoma mansoni, it probably spills over from cattle populations during a mutation event and infects our hominin ancestors approximately 5 million years ago. So the key point here is when our ancestors drank from snail-infested freshwater, standing freshwater, they got infected. Now there's a couple of key players here. Obviously humans, we're one of them. We need to be in that environment. But Schistosoma mansoni also, it has or thrives in an intermediate species, a snail. So there's a couple of species here involved. Let's move to the next slide and I'll show you exactly what I mean. Let's take a look at the life cycle of the Schistosoma helminth. Now imagine, number one, we have a human in the center there. I don't need you to remember all the details here, just the general concept. So whether it's a human or an infected hominid, we have eggs, number one, being shed from an infected human or hominid into the water. So excreting in the water, urinating in the water, all of that's going to lead to that larva eventually hatching and then infecting. Number three, snails. Snails are a necessary part of this cycle. The Schistosoma helminth completes part of its life cycle in there. So eventually it emerges from these infected snails, and we have a free swimming form from the snail that's been released into the water, and now it's in an infectious stage again. So any human moving into this water or hominid, either to drink, to bathe, to cool, has a potential of getting infected through a wound, through one of the genital meatuses, or through the mouth, for example, or nose, any way that these flukes can get into the body. From there, the human now is infected, it's penetrated the skin, and it begins to circulate through the human body, causing infection in a number of different areas. Eventually, we start to get the development of a mature worm or helminth, and it mates, lays more eggs, and that is number one, again, excreted or shed back into the water, and the cycle continues. One of the things to remember is, while we may have had limited sources of water that were infected, as ancient hominids and humans began to create, for example, devices to carry water with them, say leather sacks, that would have been responsible also for helping these helminths migrate from one water source to the next water source. Let's take a look at the next infection. Let's move to the next slide. I had also pointed out that the environment and the climate of the Pliocene was also conducive for the spread of disease through vectors such as mosquitoes or tsetse flies. So looking at this, if we look at mosquitoes from an evolutionary perspective, they're 150 million years old. The protozoa that's responsible for causing malaria, its ancestor appears to be 50 million years old. So this stuff was certainly around. The question is, could it infect our hominid ancestors, such as the Australopithecines? Evidence suggests that around 5 million years ago, there was a spillover event from other great apes, gorillas, for example, and our hominin ancestors were infected with Plasmodium falciparum. Other possibilities refer to the existence of trypanosomiasis as well. So with respect to vectors, we have to understand that the environment of Pliocene Africa, it was optimal for vectors, insects such as mosquitoes and tsetse flies. That stuff was around. And if we look at the plasmodiums, and if we look at the protozoas, for example, we also understand that that stuff had already evolved. So let's look at an example here, trypanosomiasis. It evolves 500 million years ago, this particular type of protozoan form of life. And the tsetse fly, it evolves 150 million years ago, well before our ancestors. So there's a lot of evolutionary time there for it to continue to develop, and especially into a form that's eventually going to infect us. Let's move to the next slide. Here we have another infographic from the CDC that lays out the life cycle and stages of infection with respect to trypanosomiasis. Now we have two different types of trypanosomiasis here that are discussed in our textbook as well. We have Trypanosoma brucei gambinese and Trypanosomiasis brucei rhodesiense. Rhodesiense is transmitted from cattle, ungulates, so that type of a bovid, that's where it originally emerges and spills over to human populations. We can still pick this up from cattle via the tsetse fly, and then the other form, Trypanosomiasis brucei gambinese, that's only transmitted between humans via the tsetse fly. So let's go through this in the same way, and I'm just going to highlight a couple of important points. So let's assume that we have a tsetse fly that's infected and it takes a blood meal from a human. In the same way that mosquitoes are responsible for transmitting malaria, for example, through their proboscis, they inject a little bit of an anticoagulant in the case of the mosquito, and in doing so, they're also injecting a little bit of that protozoan form of life that's responsible for malaria. Pretty much the same thing is happening here with the tsetse fly bite. So in that saliva, it's injecting some of that protozoa, and that protozoa goes on to continue to develop within the human. So again, we have a relationship here between a number of forms of life. So we have the mosquito. It's transmitting a protozoa that's going to complete part of its life cycle in a human. And in the first case of trypanosomiasis brucei gambinese, that's the only place that it can complete its life cycle. So it tells us that there has been an adaptation over time. Once it continues to develop, we have another tsetse fly, for example, that may not be infected, and it takes a blood meal from an infected human. And now that protozoa, it continues to develop. We can see in the red circle there, the red half a circle, it continues to develop in the mosquito, sorry, the tsetse fly, and the cycle continues. So African trypanosomiasis or African sleeping sickness, this continues to be a problem to this day in Africa. And I think, the other thing that's important to point out here, we've talked about bioculturalism. We're playing a role in shaping this epidemiological landscape today, for example, with clear cutting and the development of palm farms. So this continues to be a big issue, and we still grapple with it on a biological and a cultural level as well. Let's move on to the next slide. We've got the role that water and schistosoma has played in the epidemiological landscape in prehistoric times, say 5 million to 2.5 million years ago. And you can imagine that continues. We're always drinking from these water sources, and the distribution, it just continues to get greater and greater and greater as human populations become infected and we continue to infect more water sources. Similarly, we've taken a look at the role that the environment plays and the availability of disease as distributed through vectors such as mosquitoes and tsetse flies. We also have a behavioral change that takes place around 2.5 million years ago. We began to eat meat. Our ancestors did. The Australopithecines, the evidence suggests that they were not meat eaters, maybe from time to time. However, we know that Homo habilis, that was a meat eater, so too was Homo erectus. So meat, it appears to become at least a very regular part of our diet around 1.7 million years ago. There's no question about that. Earlier, we were scavenging whenever we could. Now, the problem with meat and animals is really related to worms. They carry a variety of organisms in there. Cattle, for example, they carry forms of tapeworms and roundworms. The same can be said of pigs and fish as well. So we do need to be cautious. I know from time to time we like to eat beef tartare, for example, raw meat, sushi or sashimi, freshwater sources. We need to be careful about because there are worms in that material, in that flesh. So with the regular consumption of meat, the prevalence of worms begins to increase among our hominid ancestors. And it really doesn't go away. It just persists through time. Let's move to the next slide. Here we see an infographic from the CDC on teniasis, and there's actually 3 types. We're going to talk about 2 of them, but I'll point out 3 of them. We have T. saginata, which come from cattle, bovid, or ungulates. In addition to that, we have T. solium, which is something that develops within pigs, and we have Tenea japonius, or T. japonius, which develops in fish. And in each one of these situations, The problem ultimately becomes when we consume the flesh, the meat, the musculature of any of those three animals, cattle, pig, or fish, and that stuff hasn't been cooked properly or it's been eaten raw, we consume a cystic form of the Tanea organism, and it continues to develop in us. So let's run through this model. Like I said, I don't need you to remember all of the details, just the general concept of what's taking place. So number one, we have eggs, and they exit the body. They're shed through feces and they're passed into the environment. Now, any animal, and this includes hominids, any animal that's eating vegetation, cattle or pigs, for example, they can become infected by ingesting the vegetation that the feces and these eggs have been contaminated with. From there, the eggs, they continue to develop inside of the animal in question, this intermediate species, and then they move into the muscle. And as they've moved into the muscle, as pointed out, they're in the cystic form. And if we don't cook that muscle, if we eat the meat raw, in the case of, for example, freshwater fish or cattle or pig, we will become contaminated with this cyst, and it will continue to develop into a tapeworm in a human. So from there, this attaches to the wall of the intestine in a human, and from there it lays eggs, they're shed, and the cycle continues. Now, this is pretty old. This has been going on for a long time, as pointed out, ever since we started eating meat, roughly around 2.5 million years ago. One of the behavioral changes, and we'll talk more about this because anthropologists have said really this is one of the things that has made us human. It also made us healthier. It was cooking. So at that point of time that we stopped eating raw meat and we started to eat cooked meat, our health probably improved. Now, tapeworms, they don't have a significant impact on us. And really interestingly, I think, just so you have an appreciation of how many people have worms, well over 2 billion people on the face of this earth have some form of worm. Okay, let's move on to the next slide. I hope I didn't scare you. Let's wrap this segment up with a brief review of disease during the Pliocene. And like I said, you want to make sure that you've read Chapter 7. Disease, as pointed out, it certainly existed among the Australopithecines and Homo habilis. To suggest that no disease was around would be naive. It would mean that we live in a vacuum. That's just not the case. Disease was certainly around. Really, the question comes down to how much disease was in fact around, and how did the environment and behavior support that distribution of disease, or the morbidity, the prevalence of disease. So we had pointed out that water was a great source for schistosomiasis, and that dates back to about 5 million years ago. We clearly understand that that would have been a regular infection that would have occurred. In addition to schistosomiasis and water sources, the general environment would have been conducive to malaria and trypanosomiasis as well. Diet, we had pointed out Tanea worms. We can also add ascarid worms. Chapter 7 talks about that. As we began to eat meat, we weren't cooking it in our first stages, as pointed out already, and that would have provided the opportunity for tapeworm infections. As for the majority of diseases that we see today, now we need to be careful. Again, it would be naive to say that no hominid was ever infected with, for example, a coronavirus. Possible, most definitely, depending upon the environment that they were in, it would have taken place. But again, we need to remember what I had said about small group size. In small groups, any new disease that emerges, it's going to wipe them out, and it's going to do so quickly if it's highly virulent. And in doing so, it wipes itself out. The other point is, with smaller populations, if they're not in regular contact with each other, they're not going to provide an opportunity for the survivors who may be carrying a virus to pass it on to a new group. So again, the odds of it persisting through time is highly unlikely. So we can say that there's no tuberculosis, no smallpox, measles, influenza, coronaviruses, at least in an endemic situation. So if there is any, it died out and it didn't become endemic or situated within a population. Now things are going to start to change. As we see that populations start to come into greater contact with each other, as they increase in size, we're going to start to see disease move from an occurrence, occasional, that may have drastic or devastating consequences for a hominid troop, to something that becomes a regular issue that humankind has to deal with. So we're going to explore that a little bit later on. Let's leave it there. Look for the next episode. Take care.